Standard instructional design breaks complex subjects into isolated, bite-sized micro-lessons. Real-world professional environments require complex learning, demanding the simultaneous integration of knowledge, skills, and attitudes. However, shattering an interconnected discipline into disconnected pieces destroys the essential relationships that make the system actually function. This atomistic approach works for simple linear procedures, but it collapses when applied to complex professional skills. This collapse produces a specific symptom known as the transfer paradox. Learners score perfectly on isolated module quizzes, yet find themselves paralyzed when confronted with unpredictable, real-world tasks. In complex environments, the connections between elements are often more critical than the elements themselves. Atomistic design creates three systemic pathologies within an educational program. Compartmentalization builds an artificial wall between academic theory and practical context, leaving learners unable to map abstract concepts to reality. Fragmentation occurs when a continuous process is sliced too thin, causing the learner to lose sight of the overarching logic and the big picture. The transfer paradox serves as the final consequence of this process. As the connections dissolve, the relational context is lost. Achieving high knowledge transfer requires pivoting to a holistic, whole-task methodology. Organizing training into whole tasks of expanding complexity draws these elements back together. The scientifically validated framework for this shift is the four-component instructional design model, or 4CID, developed by Jerome van Marienboer. Meta-analytical research confirms a 0.79 Cohen's d effect size on a student's success with complex tasks when using this model. 4CID re-engineers how a learner's cognitive resources are allocated during the training process. This re-engineering is based on the biological realities of cognitive load theory. When processing novel information, working memory faces severe capacity and duration limits. Complex tasks generate a massive influx of data that overwhelms this funnel, leading to cognitive failure. The brain bypasses this bottleneck using mental schemas, housed in the nearly infinite capacity of long-term memory. Fusing related data points into a cohesive mental schema allows the brain to process them as a single unit. These schemas allow working memory to handle massive arrays of information by treating them as a single, familiar element. Professional mastery requires the structural construction and automation of these schemas in long-term memory. During learning, three distinct types of cognitive load compete for space in working memory. Intrinsic load represents the natural, unavoidable complexity of the material itself. 4CID manages this by organizing whole tasks into progressive task classes. The model uses simplifying conditions that scale in complexity without breaking the task into isolated pieces. Extraneous load is wasted mental effort caused by poor instructional design, confusing interfaces, or irrelevant assignments. 4CID neutralizes this load through temporal alignment of information and fading instructional scaffolds. Temporary supports attach exactly when needed and then fade away as the internal cognitive networks stabilize. Germane load is the productive cognitive effort required to construct mental schemas. 4CID maximizes this productive effort by intentionally injecting high contextual variability into the task classes. The model operates like a precise cognitive thermostat, keeping total mental load under the biological limit while funneling energy into schema creation. A complex professional skill is split into two distinct categories of action. Non-recurrent aspects involve unpredictable situations requiring reasoning, problem-solving, and adaptability. Non-recurrent environments are characterized by constant, unpredictable flux. Mastering these tasks relies on building flexible cognitive schemas. Recurrent aspects involve routine, standardized operations that must be executed identically across all situations, requiring flawless, repetitive execution. Mastering these tasks requires total rule automation rather than deep reasoning. Because flexibility and automation require opposite cognitive mechanisms, a single pedagogical approach fails to address both. A four-component architecture is required. The 10-step design algorithm of 4CID is an engineering process used to populate four distinct architectural components. This matrix translates the theory into a concrete blueprint. Learning tasks are the highly variable whole task scenarios, forming the backbone of the program. They are measured by the integration of global skills in practice. Supportive information bridges prior knowledge to the non-recurrent aspects of a task. We assess this by testing the depth of understanding and reasoning. Procedural information provides just-in-time guidance for recurrent operations, assessed by algorithmic accuracy and strict compliance. Part task practice involves the isolated drilling of specific subskills until full automaticity is achieved, measured by speed and zero error rates. Course developers must map user activity data against these 4 components to ensure assessment metrics reflect true professional competence. The 4CID model engineers holistic environments where knowledge, skills, and attitudes are inextricably linked from day one, addressing the transfer paradox at its root.